Hi there. In this video, I'm going to try and give the most simplest explanation possible of what exactly is convolution, what is the convolution theorem, and I'm going to do it in the context of Laplace transforms. So if you go to many different textbooks and resources on the internet and many other YouTube videos, what you would see is that convolution is given as this f star g, and it's equal to this integral from 0 to t of f of tau times g of t minus tau, okay, that's t minus tau, d tau, and then somehow the Laplace transformation is taken of this, and this leads to some results which are used in a variety of different ways and so on. So when I was first starting to study this or learn this, my first question was, what is this supposed to be? What does this even mean? What is convolution? What are these two functions f of g? Why are they being combined in this way? Why is this integral being taken? What is the significance, the relevance, and the context of this convolution? And why is it being studied with Laplace transforms? And what does this even mean? So I'm going to try to explain all of that in a very specific way, just using a simple analogy. And that analogy is of this drawing that you see on the right hand side, which is that of a container that's being filled up with water from this tap. So this tap is open and there's a fixed rate of water that is filling up this container, but this container has a hole at the bottom. And of course that means that water is draining from this hole. So we're going to try to show this entire scenario, model it with a few curves and whatnot, and try to see how convolution comes out of this scenario. So firstly, let's look at this water filling up this container from this tap. So we said that it's open and the water is coming out at a fixed rate. So this is what you see on the left hand side. You can see that the number 5. So this means at 5 liters per hour. So water is coming out of this tap at 5 liters per hour, and it's fixed. It doesn't change with time. So we're going to call that f of tau, where tau is also time. It's kind of a dummy variable, tau. And let's just say there's no hole. So the hole is just blocked up there. So if we wanted to find out how much of water is inside this container, since it's a rate on the y-axis here, all we would do is we would take this area underneath this curve. So this area underneath this curve will tell us how much of water is inside this container. So we have 5 liters per hour filling up this container, and we have, let's just say 2 hours. So let's just say after 2 hours, there will be 10 liters inside this container. But this is obviously not true. The water inside this container after 2 hours is going to be less than 10 liters because the water is draining out of this hole. So we have to somehow adjust or correct this function, this f of tau, such that we are able to get a correct and true reflection of the amount of water that is inside this container. So how are we going to do that? How we're going to do that is we need to develop some kind of relationship for the water that's draining out of this hole. So what we're going to do is we're going to close this tap. Okay, we'll close this tap and there's now no water coming out of this container, so it's 0. Then what we're going to do is we're going to create an impulse. An impulse is going to be that we quickly open this tap and there's a surge of water that comes out, and we just close it quickly again. Open it, let a quick surge of water come out, and then close it. And then we take that surge of water and then we track at what rate did that surge of water drain out of this hole. So that's a question that we're asking. And if we do that, we find that we get this curve that is drawn in red here on the left. So when the surge just happens, the water drains out quickly. Okay, it drains out maybe at 1 liter per hour. But then as this water level reduces, as more of it drains out, we find that the rate at which it drains slows. So that's what we see actually in reality. So this is kind of like an exponential decay. So this is the rate at which water drains with time. So if we now wanted to suddenly get an idea of how much of water is inside this container when the tap is open, we have to somehow adjust this blue curve, this f of tau, by this red curve, which we will call g of t. But firstly, we have to move this g of t to be in line with f of tau. We have to make these two curves to be in the same place, right? So we have to kind of shift g of t. We have to move it here, and then we have to redraw it to be directly below f of tau. And now if we somehow combine these curves and adjust this f of tau using this red curve, then we'll get an idea of the amount of water, the correct amount of water that is inside this container at a certain amount of time. That is what is convolution. That is what convolution is. Convolution literally means where we take two functions and we combine it together such that we can get some kind of property out of doing that. But let's just do that quickly in terms of moving this red curve to be directly below the blue curve. So there it is, right? So there we have f of tau, and then here we have g of t minus tau. So it's t minus tau because we have shifted that red curve. So we have shifted it t minus tau units. Now it's here, right? So f of tau is this water if representing it filling up this container. So we'll say filling up. And the red curve represents draining. Now we have to adjust this curve, okay? We can see that for the red curve, all the values are less than 1 because it's a decaying function. So if we combine these two curves, we're going to get exactly how much of water is inside this container at any given moment in time. So we have to multiply them, right? That's what we have to do. So if we multiply them, we get a curve that looks like this. So multiplying it, if you think about it, we have 1 and we have 5. So if we have 1 times 5, so it's going to be 5. So the curve will start off at 5. And then all the values are less than 1, right? All the values of the red curve are less than 1. So if we multiply at each point this red number by this blue number, we're actually adjusting this blue number. We're bringing it lower such that it correctly reflects the rate at which water is accumulating inside the container. So this orange curve, which is now drawn on the right-hand side here, it's just isolated here, is actually the product of these two functions. So it's f of tau times g of t minus tau. And remember, if we just go back up, and you see here, we said that if we wanted the amount of water inside the container, we have to take the area underneath this curve. So it's the same thing. If we want the amount of water inside the container, we have to take this area underneath this curve. That's why it's not just enough just to take the product of these functions. We have to integrate this function between 0 to t, where t is some arbitrary time. And our integration variable is d tau. So this is convolution. This is what this convolution equation, that's why it looks this way. It looks this way because we have two functions, f and g, and we have to multiply them to get this idea of the correct amount of water that is filling up inside this tank, and we have to multiply them to scale or adjust this f of tau to make it this lower value such that we get this orange curve, and that orange curve is the product of these two functions which we have to integrate to get the actual amount of water inside the container. And that act of these two curves interacting and combined in this way is what is convolution, and is depicted with this notation f star g. So that is convolution. So this is a very important concept, and it's used in a lot of different fields of process control and control theory and so on. But in any way, what we're now going to consider is the Laplace transform of convolution. And it leads us to a very interesting result, which we will analyze, and then we will just try to use this result to see the value in doing that. Firstly, let's just remind ourselves what is the definition of the Laplace transform. If we take the Laplace transform of some function of t, then what we're doing is we're taking the integral from 0 to infinity of that function f of t, and we're multiplying it by e to the minus st dt. So now instead of f of t, we have this Laplace transform of convolution. So this f star g. So we just replace this f of t with that integral. So what's going to stay the same? So what's going to stay the same is this e to the minus st dt. However, instead of f of t, we now have convolution, and that convolution is integral from 0 to t f of tau times g of t minus tau times d tau. So we're going to proceed with this derivation, and it's going to lead us to this interesting result. And the first step to do that is to actually interchange these integrals. So this inner integral is going to become this outer integral, and what is this outer integral is going to become this inner integral. And in the process of doing that, there is some change in this integration boundaries. So this inner integral is tau going from 0 to t, and this outer integral is t going from 0 to infinity. So let's write that. So we have t going from 0 to infinity, and we have tau going from 0 to t. So let's just think about t for a second there. So t is, you can see that it's less, okay, it's more than 0, right? It's between 0 and infinity, but this second kind of inequality says that t is actually more than tau. So the lower boundary of t is actually tau. So we just have to isolate that part and understand that. And the upper boundary is still infinity. Then if we think about tau, tau is going from 0 to t, right? So that 0 is not going to change. It's still going to be 0, the lower boundary. But if it's being less than t, and then t can go all the way up to infinity, it means that the same is true of tau as well. So that's how these boundaries change. So we have to update these integration boundaries to reflect these new boundaries. So we swap these integrals now. So we have this integral from 0 to t, no longer 0 to t. So it's going to be 0 to infinity. And this is with respect to tau, and we're making tau the outside integral. However, f of tau can actually come out because it is only with respect to tau. We can write that. And then d tau becomes the outside integral. So we'll write that here. So now we have the inner integral, and that is t going from 0 to infinity, but however we now showed going from actually tau to infinity. And what's left is just g of t minus tau times e to the minus st, e to the minus st d tau. So we're just going to take out this inside integral and evaluate that. So let's just write this inside integral. We have integral from tau to infinity, g of t minus tau times e to the minus st. Sorry, this should actually be a t here, times dt. What we're going to do is a substitution, and the substitution is that u is going to equal to t minus tau. So that means that du is going to equal to dt, and that t will equal to u plus tau. Also, these boundaries will change, so t is going from tau to infinity. So if we substitute tau inside here, it means that the lower boundary is going to be 0, because tau minus tau will be 0, and this infinity won't change as the upper boundary. So let's write this in terms of u. So we have the integral now of u going from 0 to infinity. Then we have g of u times e to the minus st. However, t is u plus tau. We'll just incorporate that. Then we have du, because dt is equal to du. We can just separate out this exponents. So we have this integral from 0 to infinity of g of u times e to this minus su times e to the minus s tau times d of u du. However, since this integration variable is u, both s and tau are constants inside this integral. So we can actually bring this e to the minus su out of, s tau out of it. We can write it out of the integral. So it becomes e to the minus s tau here. And this du, we can just write it a bit closer. But now, look at what we have. We have integral 0 to infinity, some function times e to the minus s of that function variable. Let's look at the definition of the Laplace transform. It is literally the exact same thing. So what we're saying that is this term here is the Laplace transform of g. So that's our important finding here for this inner integral. This thing becomes e to the minus s tau times this Laplace transform of g of t. U and t are of the same quantity. Remember that tau is a constant here. So it's literally, the u is basically in the same dimension as t. We can take this result and substitute it into our convolution equation that we have written here initially. So this inner integral is basically this e to the minus s times tau times the Laplace transform of g. So we're just going to take that and we're going to complete that. So we're going to take this and we'll write it here. So the Laplace transform of this convolution is equal to this integral from 0 to infinity. Then we have f of tau. Then we have e to the minus s tau times this Laplace transform of g of t multiplied by d tau. And if we now consider this, what is that? That is just the Laplace transform of f. It's of the same format of our definition of the Laplace transform. So what this means is that this relation now becomes the Laplace transform of f of t times the Laplace transform of g of t. So this is actually what is called the convolution theorem. It's incredibly important because it allows simplification of a lot of different kinds of equations that we would normally have a lot of difficulty doing. What I mean is that we have to take functions and we have to compute the product of these functions and integrate it. Think about it, integration from 0 to t of f of this function times g of this function. It can become quite difficult to evaluate this integral. However, we can say that this integral is the same as finding the Laplace transform of f, then finding the Laplace transform of g, then multiplying the two, and it will give you the Laplace transform of the convolution. And then just by finding the inverse Laplace transform of what we get here as the result, it will give us this convolution. So that is the amazing finding here. It's very easy to find Laplace transform of functions and then to take the inverse as opposed to try to evaluate some kind of difficult integral. So let me illustrate what I'm talking about by a simple example. We can have f of t equal to sine t. Then we can have g of t equal to e to the minus 2t. So if we want to take the convolution, this f star g, what we would need to do is we'd have to integrate from 0 to t. And now this f of t becomes f of tau. So we would have sine of tau times g, I'll just write it here at the top, f of tau times g of t minus tau. So this becomes e to the minus 2 into t minus tau. And then we need to integrate this with respect to tau. So this is not really that difficult an integral. It's kind of manageable. We would have to use integration by parts, but it would take us quite a long time. There would be quite a number of steps involved in doing this. So it's probably much easier to use the convolution theorem. And the convolution theorem says that we just take the Laplace transform of f and g, then we multiply it together, then we take the inverse of that result, and we get this convolution. So let's try that out. So firstly, the Laplace transform of f of t is equal to just the Laplace transform of sine t, which you can just check in your standard transforms, and then you can see it's 1 over s squared plus 1, and then the Laplace transform of g of t, that's simply equal to 1 over s plus 2, again using the standard transforms. So this Laplace transform of the convolution is equal to just the product of these two quantities that we have just written now. So it's 1 over s squared plus 1 s plus 2. So to find the convolution, all we have to do is just take this inverse transform, inverse Laplace transform of 1 over s squared plus 1 s plus 2. So this is a very straightforward thing to do using partial fractions. I've illustrated this in previous videos. So all we have to do is we take 1 over s squared plus 1 s plus 2, and then what we do is we say that this is equal to, when we break it apart, we have a over s plus 2, then we have plus bs plus c, where these a, b, and c are coefficients we have to determine quickly, and this is divided by s squared plus 1. And then we take these two equations, multiply both sides by this denominator that's on the left. We get 1 is equal to a into s squared plus 1, then we get plus bs plus c into s plus 2, and then if we expand the right hand side out, then we get as squared plus a, then plus b times s plus s, which is s squared, then plus 2bs plus cs plus 2c. We just group some of these coefficients. So we have s squared here into a, then plus b, then we have plus s into 2b, then plus c, and then lastly we just left with a plus 2c. We just equate these coefficients. So we have a plus b, well, that's equal to 0. There's no s here on the left hand side. So that's also true with 2b plus c. So 2b plus c is also equal to 0. Then we have a plus 2c a plus 2c, that's equal to 1. So we can solve this quite easily. So if a is equal to b, that means that b is equal to minus a. So that means that here c is equal to minus 2b, and if b is equal to minus a, c is equal to just 2a. Then that means that this equation becomes a plus 2 times c, and then c is equal to 2a. So we have 2 times 2, which is 4, so we have 4a equal to 1. So this implies that a is equal to 1 over 5. And then we can carry on in this manner. That means that b is equal to minus 1 over 5, because b is equal to minus a. And then c is just equal to 2 times a, so that's just 2 over 5. So substituting all of these things inside our partial fractions, what this means is that our 1 over s squared plus 1, s plus 2 was equal to a, so a is 1 over 5. So we have 1 over 5 into 1 over, so that's a 5 not an s. We have s plus 2. So we had bs plus c, so this b was minus 1 over 5, so we can have minus 1 over 5. And we can divide each term, bs over s squared plus 1, so that that will give us s over s squared plus 1 and then we have plus c over s squared plus 1. C was 2 over 5. We have 2 over 5 into 1 over s squared plus 1. If we take the inverse Laplace transform of this, we just do it of each term. We take the inverse transforms, which you can also refer to in the table. So for this first term, 1 over s plus 2, we know that the inverse transform of that is just e to the minus 2t. We have 1 over 5 in front. And s over s squared plus 1, that's just cos t. So we have minus 1 over 5 cos t. And then we have 1 over s squared plus 1. Sorry, that was s over s squared plus 1. So this is 1 over s squared plus 1. And that is just sine t. So we have plus 2 over 5 sine of t. So this is convolution. So this illustrates the procedure of how we can use this convolution theorem to get what the convolution is just by applying these Laplace transforms in this manner. So this video firstly started off by giving an explanation of what is convolution to begin with, because that might not be explained in all of the places of reference. And we use this analogy of this tap filling up this container. We saw that we have two functions and we want to capture the interaction between these two functions. In other words, the amount of water that is in this container at any given moment in time. We have to correct the amount of water coming out by the water that is being drained out. And we do that by combining these two curves. And then we actually have to take the area underneath this combined curve to get that water inside this container. And that is actually what convolution is. Then we proceeded to find the Laplace transform of this convolution with this derivation. And the result of that was that we showed it's the product of these two functions. It's this Laplace transform of the convolution is simply the product of the Laplace transform of these original functions. and we can use that property to actually find many different kinds of convolutions that would be quite difficult to find by using normal integration techniques. And this example that we looked at was sine t and e to the minus 2t. We found the Laplace transform of each of these functions. We multiplied it, then we just took the inverse Laplace transform using these partial fractions, and then we were able to find the convolution in this manner. So thank you very much for watching.